Have you ever wondered how we build things so small they're literally invisible? We're talking about the ultra-thin materials that power, well, pretty much everything in our modern world. Today, we're diving into the incredible technology that makes it all possible: chemical vapor deposition, or CVD for short.
All right, so here's what we've got on tap. We're going to start with the basics. What even is chemical vapor deposition? Then we'll get into the nitty-gritty of the process itself. After that, we'll look at how scientists are able to master it, touch on some seriously cutting-edge versions of this tech, and finally, we'll see why it matters so much to, well, to all of us.
All right, first up, what in the world is this process that lets us build stuff at the nanoscale, stuff we can't even see with the naked eye? Okay, so at its core, you can kind of think of CVD like a super precise baking process. Seriously, you take these special gases, we call them precursors, and you pump them into a chamber. These gases are your ingredients. They react with each other and poof, they deposit a solid, perfectly thin film right onto a surface. It's like baking a cake that's only a few atoms thick. And what's so cool about this is that CVD isn't just, one thing. It's not just chemistry. It's this incredible mashup of a bunch of different scientific fields. You've got thermodynamics dictating if the reaction will even happen. You've got fluid dynamics dealing with how the gases flow. And then you'll have the really complex surface science, figuring out how those atoms actually stick and build up that layer. It's a true team effort of physics and chemistry.
So, how does this actually work? Let's break down the core process from gas to solid, step by step. Think of it like a perfectly timed 4-step dance. Okay, step 1, you've got to get the precursor gases delivered right to the surface you want to coat. Step 2, the gas molecules have to actually stick to that surface. That's called adsorption. Step 3, and this is the magic moment, the chemical reactions fire off and the solid film starts to form. And finally, step 4, you got to clean up. All the unwanted gassy byproducts get swept away. Getting every single one of these steps just right, that's the whole game.
Right. So this isn't some random chemical soup. Oh no. Scientists and engineers have this process on lockdown. It's like they're sitting at a high-tech control panel with a bunch of dials and levers they can tweak to get exactly the material they need.
And what are those levers? Well, things like the substrate temperature, the pressure inside the chamber, the purity of the chemicals you're using, even the exact recipe of the gas mixture. By fine-tuning all of these, you can control literally everything. How fast the film grows, what its structure looks like, you name it. And talk about control, sometimes this means cranking up the heat to insane levels. For some ceramic coatings, we're talking 900, even up to 1400 degrees Celsius. That is seriously hot.
But there's a problem, right? What happens when you're trying to build something delicate, like a computer chip? That kind of heat would just fry it. So this major challenge led to a really clever solution. What if you didn't need all that heat? What if you could add a spark?
And that's where this next idea comes in. Plasma enhanced CVD, or PECVD. It's a total game changer. Instead of just using raw heat to get the chemical reactions going, you use a plasma. Now, what's a plasma? It's basically an energized gas zapped with electricity. This plasma creates these super reactive molecules that are just raring to go, and they'll form that film at much lower temperatures. This makes the whole process way more flexible.
Okay, so that's already pretty precise. But what if we could get even more control? What if we could take this to the absolute limit? We're talking about painting with individual atoms. This is where we get to something called atomic layer deposition, or ALD. And that painting with atoms idea, that's literally what this is. ALD is a special type of CVD where you break the process into these separate, sequential steps. You introduce one chemical, let it react with the surface, clear it out. Then you introduce the second chemical, let it react, clear it out. Each full cycle lays down exactly one perfect layer of atoms, one single layer. That one layer at a time thing is the secret sauce here. It's called a self-limiting reaction. That means the reaction just stops on its own once the entire surface is covered. It can't build up more than one layer. This gives engineers just an insane amount of control. It also leads to this property called conformality, which is a fancy way of saying the coating is perfectly uniform. It perfectly follows every tiny nook and cranny of a complex 3D shape, like shrink wrap at the atomic level. It's amazing.
Okay, so this is all really cool science, but so what? Why should you care? Well, because these atom-thick, perfectly built films aren't just stuck in a lab somewhere. They are the invisible, unsung heroes inside the technology you are probably using to watch this right now.
If you look back, CVD started out as this kind of niche technique back in the mid-1900s. But then the 80s hit, and the computer revolution needed a way to build microchips, and suddenly, CVD was indispensable. Fast forward to the 2000s, and with things like ALD, it's what allowed us to build the crazy complex 3D chips we have today. And now, it's the go-to method for creating the next generation of supermaterials. And its impact is just massive. It is the absolute engine of the entire semiconductor industry. But it's not just that. We use it to make super tough protective coatings for everything from drill bits to jet engines. And of course, it's our main tool for actually creating brand new nanomaterials from scratch.
Seriously, just think about the computer chip, the brain, inside your phone, your laptop, your car. All those billions of tiny transistors are built up layer by layer. And the critical insulating layers that keep everything from shorting out, those are almost all put there using CVD. It is no exaggeration to say this is the process that builds our digital world.
And it's not just about tiny electronics. On the other end of the spectrum, CVD is used to create these unbelievably tough ceramic coatings. We're talking about films that make cutting tools slice through steel like butter or allow jet engine turbine blades to spin in hellish temperatures without melting. It gives them the superhero-level toughness they need to survive.
So, what's next? Well, this is where it gets really exciting. CVD is at the absolute forefront of creating the materials of tomorrow. You've probably heard of graphene, right? That wonder material that's a sheet of carbon just one atom thick. Well, how do you think we make big, high-quality sheets of it? Yep, CVD. This is the key that's going to unlock next-gen flexible electronics, hypersensitive sensors, maybe even quantum computers.
So when you boil it all down, chemical vapor deposition has gone from being just a chemical process to a full-blown platform for designing our world at the atomic scale. We literally have the power to build things up, atom by atom. And that leaves us with a pretty profound question to think about, doesn't it? As we get better and better at this, what new materials, what new technologies, what new worlds will we decide to build? Thanks for joining me for this explainer.